Um, so if that ever stops bouncing, that's my, like, if that, yeah, if that ever stops bouncing, that's bad news. Hopefully it won't. Okay, so let's get started in here. I mean, you said we already started. Where you been? But so this, what you just did, of course, is just like a quick review of differentiation and those basic integrals, right? So for the most part, except for maybe like the last two on that, you should have been able to just kind of write down the answer, right? So if you couldn't just write down the answer, it just means that you're missing one of the like preliminary facts in this course, right? From the last course, and that's okay, but that's why I'm giving you the quiz so that you can kind of adjust and fix what you're missing, right? Because you don't really know what you don't know until you have something where you can't open up the book and look up stuff, right? And you can't open up the book and look at stuff on the test, so I think it's important for us to have these quizzes to just kind of help you to gauge what you actually really understand versus what you're, I mean, there's different levels of understanding, right? Like, we can all I mean, I can do really, really complicated stuff if you give me books and time, right? But if you just ask me to do those things from my knowledge, then I can't do them, right? Because I don't know that stuff. So our goal in this course is for you to know calculus when you leave. So, you know, and I don't think anybody really learns Calculus 1 entirely in the course, like very few people. It's usually in the process of taking Calculus 2 that it really settles in. So I'm sure many of you have different starting points. Do not despair if you did bad on this quiz. Like this is a tool to help you improve, right? That's what all the quizzes are. And you notice that there were 11 questions. They're each worth 10 decipoints. I'm doing that so I can take off like 1 decipoint if it's like a little bit wrong, because I hate, like, fractions are trouble, right? I don't know, I mean, adding fractions, doesn't matter how old you get, it's still, you know, takes effort. If I use decipoints, then I can grade, basically I'm grading your quizzes on 100, but that 100 is actually 10 points, yeah? So the conversion rate's simple. What that means is there's like basically 10% bonus on this quiz. So if you got it perfectly right, you could have earned basically 110% on this one. And if you simplified your answers in ways that I think are really, really nice, I might even give you like a bonus beyond that. We'll see, right? But, okay, so let's get started. Today's topic, after I write this here, I should ask you, are there any questions about the, where we're going, what we're doing? I forgot to start the electronic book for you guys last night. I'm sorry about that. Although working against me doing that, because I know that if I can procrastinate things, I will earn respect in the eyes of some of you. And so somebody in my physics class mentioned that they could find the physics book through Cengage Unlimited. Is it possible to do that with the calculus book as well? So we should do that. So you don't need the WebAssign access. You can look it up through the Cengage Unlimited. I don't know who was asking me about that last cut. A few of you were, right? Am I speaking Egyptian? Oh, does this make sense what I'm saying? I don't think I need to start the WebAssign, the fake WebAssign course, because we can just look up the book through Cengage Unlimited if you have that. You all have that, right? Because that's part of, you know, some deal the university struck with Cengage. So you could go look up Cengage books of courses you're not even taking if you want, right? Very exciting. Okay, so integration by parts. So if that, you can come talk to me after class. If that still doesn't work for you, let me know, okay? But otherwise, I'm going to wiggle that route. So what is integration by parts? Well, there's any number of questions, right? Like if you look at the quiz, the things I asked you to differentiate, right? Some of those things, well, I still couldn't do with integration by parts. And that's one of the larger themes in this course, right? Differentiation is relatively easy in the sense that once you know it, you apply the rules, you do it, right? Integration, on the other hand, it's not the same, is it? See, because, for example, what if you were trying to integrate the inverse sine of x dx, right? How would you even do such a problem, right? Or how would you integrate x times e to the x dx, right? If you try to use u substitution to do these problems, you're going to go nowhere. I mean, you can try it, right? Like what would you make u equal? Let's not do that. I mean, let me just tell you, if you tried u substitution on these, you'd get nowhere really fast, right? And if you just try to guess the answer, there's hope. There's hope you could guess the answer on this one. But I don't think you're going to guess the answer on that one. Let's see why. So we need integration by parts for such problems. All right. So it's generically speaking, if you're faced with the integral of an inverse function, right? A lot of times integration by parts is the right course of action. If just generically speaking, if you have an integration you can't do, a lot of times integration by parts is the right course of action. So what is integration by parts? Well, let's look at it. So d dx of a function u times a function v, all right, is equal to what? It's equal to du dx times v plus u times dv dx. Right? We all can agree about that, I think. So if you take this equation, right, and you solve it for just, say, this term right here, solve for that, what do we get? We get u dv dx is equal to d dx of uv minus v du dx. I'll just rewrite the derivative being second, right? So all I've done so far, this is just product rule, right? I rewrote the product rule. Now why is this interesting? This is interesting because if we integrate this relation, we find something kind of neat. So I'll do that up here. So we have u dv dx equals to d dx of uv. I'm just rewriting the same thing down again. Minus v du dx. All right. Now let's integrate that with respect to x. Integrate with respect to x. What happens? Well, you guys know about u substitution, right? So what was the basic idea that we learned is that we can cancel the differentials and change the variable if possible, right? So like if you look at this, if we use u substitution, this simply gives us that the integral of u dv is equal to, what happens when we integrate a total derivative? What's the integral of d dx of uv? Remember, integration and differentiation are inverse processes, right? So this just gives me uv. And then I've got minus the integral of v du. So I try to make my u's like a little bit curly, and my v's really not curly at all. So you can clearly see the difference between u and v. If it was up to me, I would use different letters because I think u and v are too much alike. So like if you want to get in the habit of doing integration by parts using like a and b, more power to you, right? You could just as well write down the formula a db equals to ab minus the integral of b dA. That's more fun to say too. A dB minus is equal to AB minus integral of B dA. Anyway, so however you want to package it, we usually use this one. I will always use this one because that's what everybody uses. So since I'm a conformist, obviously, I'll use that formula there. Yeah. Okay, so how does this help us? Like you're like, well, that's lovely, but what does this do for us, right? Well, let's try it out on one of the examples which I claim you can't do otherwise. And we'll start out with the easy one. Let's do integral of x e to the x. So example 1. Integral of x e to the x dx. How do we do this? So in order to do this, we need to identify what's u and what's dv, all right? So I'll just write right here to show you. Let's think of this as being dv, right? E to the x dx is dv, and we're going to make x u. So I'm going to write down here, since it's easy on the board, u equals to x. I usually write off to the right when I'm writing in by myself. You know, like when I'm writing a solution, I'll write this to the easier to write it over here and make a little box or something. So those are my choices, right? Now once I've chose u as x and dv as e to the x dx, I need to figure out what v and what du are, right? Because the formula, the box formula right above requires me to figure out both v and du. How do you figure out v if you know dv? We integrate, right? So v is going to be the integral of e to the x dx. Now, it turns out that you don't need to add a constant for this one. All right. I explained in the notes why that's true. If you don't believe me, try adding a constant, see what happens to your answer. All right. But let's not add a constant. We don't need to, it turns out. We just integrate, got e to the x. And u, that gives me du, is dx. All right. So this right here sets up the integration by parts I'm about to do right here. All right. So when I'm starting my integration by parts, I usually force myself, just as a point of good mathematical etiquette, and to help myself earn partial credit if I do things super wrong, I write this down. Okay, so at least the instructor knows like what you're doing, right? So that helps me give you partial credit if you're like way wrong. Okay, anyway, and it also helps you make the right next step. So uv, right? So we do x e to the x minus what? My v was e to the x. My du is dx, right? So at this point, we're back to something we already know how to integrate, right? So the bedrock of everything we're doing this semester to start with, it rests on you knowing the integrals from Calculus 1, right? So like the fact that you guys know the integral of e to the x is e to the x means we're home free, right? We can finish this. So here it is, the answer. X e to the x, yeah, minus e to the x, and then plus a constant. Does anybody want me to show you why it doesn't matter if we add a constant to the v or not? Yeah? Okay, let's do it. So what if we added v? So what if we had u? So we'd still have u equals to x. We'd still have, but this time we'll have v equals to e to the x plus a constant, right? Let me call it c1, c2. Then when we have the integral of x e to the x dx, what we would have instead would be okay, so uv minus integral of v du. What's that look like in this case? So that would look like x e to the x plus c2 minus the integral of e to the x plus c2 du is dx, right? So what then happens is we get x e to the x plus c2x, right, minus c2 integral of dx minus the integral of e to the x dx, which gives us x e to the x plus c2x minus c2x minus e to the x plus a constant. And this always happens. I derive it in general in the notes, but it's always the case. If you add a constant, if you had picked a different antiderivative, in other words, for your v, it doesn't matter because they cancel out as you apply the integration by parts formula. See, these cancel. It's gone. And we're back to the same answer, right? Now, yeah?
And just as clarification, correct me if I'm wrong, when you're finding du, you're taking the derivative of what u is.
Right.
And adding dx, right?
Yes. So to calculate du, we calculate du dx and multiply by dx. So this is like part of a larger story, which is like how do you take the differential of a function, right? So the differential of f, you may or may not have talked about this in Calc 1, but like this is another way to think about it. df is f prime of x dx. So that's actually my thinking. But you're right. I mean, it's the same thing as saying you calculate f prime of x as df dx and then multiply by dx, right? But I actually think of like du as a thing that I do to you. I don't necessarily think about it as du dx. But I'm not saying anything interesting here. All right. So Um, Other questions? Now, I think there's a lot of you that if I put money on the table or gave you some time, or something, some kind of incentive, I bet you could have guessed this. I think enough time passed by. Some of you are like, yeah, I had all of calculus in high school. I already know that, so haha. Or something. Maybe not, I don't know. But, it starts to be like, but that's easier than guessing it, right? This just deriving, this is the function that if I differentiate, I get back x e to the x, right? So let's take this out for a spin on the next example. Let's try it on inverse sine, see what happens there. Yeah? Can we do inverse sine? All right, so every integration by parts. So we've got to choose what's u equal to, and then, from that, we'll have our du. We need to figure out what v is, dv is, and then we can figure out what v is. So you notice, in order for us to do integration by parts, what kind of thing does dv have to be? Think about it. Like the dv has to be something you can actually integrate. Otherwise, this method doesn't help you. This was like, if I write down dv as e to the x dx, but I can't get to v equals e to the x, then I'm stuck, right? So as you look at this expression, what can I make dv? You're pretty much forced to make dv dx here, because anything else, well, that's begging the question, right? Like, we don't know how to integrate inverse sine yet, so this has to be dv by process of elimination if this is going to work, right? Short of higher order, sneakier things, which exist. But this is going to be our u. Now, dx, you can integrate, right? What's the integral of dx? I had a job interview once with a guy who told me about his advisor used to bring his grandson into Calculus 1 after like the integration test so that he could shame the students. And he'd bring his 5-year-old grandson up into the front. He'd put him up there and he'd be his son. What's the integral of dx? And he'd be like, x plus a constant, sir. And he's like, even a 5-year-old can do it. What's wrong with you guys? Because of course, this always slips past people's radar, right? Like, how do you integrate a constant, right? It's easy enough to forget that, but it's just x. Now, because we're integrating 1, right? The derivative of x is 1. So how about du? U is inverse sine. Can you tell me what we do there? What's the derivative of inverse sine? 1 over the square root, 1 minus x squared. Are you sure it's not x squared minus 1? No? You are sure. OK, that's good. And you're right, because remember that the domain of inverse sine is the range of sine. The range of sine is minus 1 to 1, right? So it has to be this. X squared minus 1 only makes sense for x larger than 1. So it has to be 1 minus x squared if we think about the range of sine. That's all it could be. If you're confused about which one it is, x squared minus 1 versus 1 minus x squared. OK, so what do we have then? uv minus integral of v du. So this gives us what? X inverse sine x minus the integral of what? X dx over the square root of 1 minus x squared. I'm going to install a light in here. Do it. Just need like one strip the whole way. But that'll always be a glare or something stupid, though, if I install it. All right, anyway. So how do you integrate that? Let me suggest we make w equal to 1 minus x squared, right? If I do that, nice things happen, see, because then dw is minus 2x dx, right? Which tells me that x dx is actually minus dw over 2. Which means I can make a substitution here, right? This gives me plus the integral of dw over 2w. By that, well, I'd say u substitution, but I decided to make it a w substitution since I already used u for the integration by parts. Yeah? Yep.
Why do you have x dx over the square root of 1 minus x squared? Isn't that just supposed to be x over that? Since it's just v du?
The v
Okay.
is the x and the du is the, yeah. It's all good. Mm-hmm. We're here 5 days a week, guys. We have time for questions, right? So just ask when you got them. It's all good. Don't mistake my speed for not caring what you think. It's just my setting. You're not going fast. Fine, fair enough. Fix that. There you go. So the integral of 1 over w is the natural log of the absolute value of w, but w is 1 minus x squared, so I plug it in. I have to add a constant at the end. Everything's said and done. There you go. At this point, I think we've reached our first answer that I can in good conscience say nobody here guesses this is the answer for the antiderivative, unless they've had previous exposure to these ideas in a calculus class, right? That's not at all obvious that, oh, yeah, sure, this is the function that you pick to differentiate to get back to here. No, there's some kind of like really interesting cancellation of factors that goes into making this the antiderivative of that. Yeah? And you'd be like, well, that's, who cares? Well, you might care if you're interested in calculating the area under inverse sine. Have I made a mistake?
Oh, just on the integral,
Uh-huh.
it's supposed to be 2 square root of w.
Ah, man. Oh, but then I don't have a natural log. I wanted a natural log in my answer. See, this is what happens when you hurry. Thank you. Sadness.
Deducting 0.2 decimal points.
You're deducting. I was thinking about converting my course to megapoints. And then like I'm trying to remember how many, if I used megapoints, well, see, no, I should use millipoints. I could give 1,000,000 millipoints in a course, right? Because each point is 1,000 millipoints. So yeah, that square root of w matters. My bad. So what's the integral of 1 over twice square root of w? This is easier. It's just the square root of w, right? So we get plus the square root of w plus a constant. Sorry about that. Pride to go with before the fall, I guess. What are you gonna tell you? X squared plus a constant. So hopefully I got it right this time. I don't know. Eventually I'll learn how to do calculus, I can tell you. Is that better? I think my claim remains, though, that like it's not obvious that that's what the integral would be, like just by guessing, right? Another? Yeah. What if we were going to do, say, integral of, let's see what's on my plan. Let's try out x 2 to the minus x for size. So as a general rule of thumb here, this is kind of like example 1, right? So probably the same strategy is going to work again, right? Like we'll make u equal to x. Oh no, I've scrambled the board. Let's see here, u equal to x. Du will be dx. dv will be 2 to the minus x dx. What's the integral of 2 to the minus x dx? What function can you differentiate and get back to 2 to the minus x? So in calculus 2, this is the kind of u substitution we'll just do in our head without writing down. Yep.
Negative 2 to the minus x divided by the natural log of 2.
Negative 2 to the minus x divided by the natural log of 2 would be correct, right? Because remember the rule for differentiating a to the x is d dx of what? A to the x is natural log of a times a to the x. Sorry, if you can't see that. So if we put 2 in, we get, whenever we differentiate like 2 to the whatever, we get a log 2. So when we integrate, we have to divide by that to be fair. Okay, so what we got is uv minus the integral of v du, which is x times minus 2 to the minus x divided by natural log of 2 minus the integral of minus 2 to the minus x over log 2 times dx, which, let me clean it up a bit. So that's minus x times 2 to the minus x over natural log of 2 plus 1 over the log of 2 integral of 2 to the minus x dx, right? But of course, if we can integrate 2 to the minus x dx once, we can do it again, right? So what happens? We get minus x 2 to the minus x over natural log of 2 plus, well, minus rather, minus 1 over the natural log of 2 squared times 2 to the minus x all plus a constant. And I suppose we could simplify this, but I think I'm just going to leave it like that because, yeah. Shall we try another? Let's try another. Any questions about this one? Again, I would point out, if you tried u substitution for this, you get nowhere. Example, am I in 4? 4, all right. How about if we try out the integral of the natural log of x dx? How's that going to go for us? Right? We've seen natural logs and answers for integrations, but we haven't seen it as an actual integrand yet, yeah? So again, I'm pretty much forced to do this integration by parts. U is natural log of x, dv is dx, right? So u is 1 over x, excuse me, du is dx over x, and my v is x, right? That's the integration by parts I'm going to do. Again, uv minus integral of v du. What happens then? This is the time of class they start to get rowdy. It only gets worse from here. Okay, so what we got? We got x. No, we got x log x, right? I'll write the x first because it looks better. Minus v, which was x. And then du was, well, dx over x. Hey, look at that. Those cancel, right? We're just left with the integral of dx, which, as we know, only a 5-year-old knows if they're properly instructed. It's like Dr. Cook said that part of the kindergarten curriculum should be integral of dx. I'm like, yeah, sure. For the purposes of comedy and grandfather's calculus classes, I'd agree with that. There it is. So the integral of log is x log x minus x. Yep.
Parentheses around the x plus c.
Nope. No. We always can, when we're integrating like this, we just add c to the end. A little bit later in the course, we'll be solving differential equations, and there we'll have to be more careful in how the c gets packaged into things. But see, like I could write minus c here, right? Maybe that's what you're thinking, and I see why you'd say that, right? But if I wrote minus c, it's the same answer, really. See, because Either way, I'm just adding an arbitrary constant. So the point of this is that this is the general class of function whose derivative is this back here, right? So whether I add a c or subtract a c, it's the same answer. So we just, you could put 2c there. I wouldn't count you wrong, you know? But anyway, OK, so yeah, example 4. Shall we do another? Let's do another. I think we know this now, right? No? All right. Let's try this on for size. Example 5. The integral of cosine squared theta d theta. So we have the integral of cosine theta d theta times the integral of cosine theta d theta, which is what? That's sine theta times sine theta plus a constant, right? I'm an authority. You must obey me. This is the truth now. You're an American. Come on. You hate science? No, this is wrong, right? This is not true. This is not how we integrate, right? Like, this is not even how we differentiate, right? When you differentiate a product, is it the product of the derivatives? It's not, right? It's what I just erased over here, right? So this is not, this is nonsense, right? So I think it's sometimes important for us to just take a breath and say, you know what? Why aren't we just doing that? Well, it's because that's not true. We have to sort of run through the product rule in reverse, right? That's what integration by parts is. We're using the product rule in reverse. So let's do it the right way. Because this problem is not like the ones we've done so far. This one's a little bit different. Now, you may already know how to do this integral a different way, all right? You're like, I can do this by a u substitution. Some of you, right? Maybe. Let's see how integration by parts solves this thing. So we do need to look at this as cosine theta times cosine theta d theta, like that, all right? So cosine theta is in the u and it's in the dv, right? We're going to look at, let's see here, u equals to cosine theta, and dv is cosine theta d theta. So that makes my du minus sine theta d theta, and that makes my v sine theta. All right? So then what? Well, then I do integration by parts, right? So I got uv minus the integral of v du. What's that here? Apparently, it is cosine theta sine theta. What's my v du? I got a sine theta. I got a minus sine theta d theta. So the plus and the minus in the formula and the minus in the du, they cancel, and we get plus the integral of what? Sine squared theta, right? Hopefully I did it right this time. The last time I tried to just do something in my head and not write it down. Today it went badly for me. But so then what? Like, well, that doesn't help, because that's just as bad as what we started with, right? Yeah?
You can convert it to the integral of cosine squared theta and plus 1.
Ah, so you're saying use the Pythagorean identity. So that's 1 minus cosine squared theta, yeah? I like that, but that still doesn't quite, so this 1 integrates to theta, right? And then we have minus the integral of cosine squared theta d theta. Oh man, we just come back to where we started again, right? But why is this a good thing? Because we didn't actually just come back to where we started again, did we? It's not quite the same, is it? Notice something different? Minus. Right? So if you take this and you just look at it from a different perspective, we're trying to find this integral I, right? Call that I. What we found is that this I is equal to cosine theta sine theta plus theta minus I. So what's I equal to? Do algebra, solve for it, right? So solving for I, we get I is equal to, well, we get 2I is equal to cosine theta sine theta plus theta, which is to say that I, which is the integral of cosine squared theta d theta, is in fact 1/2 of cosine theta sine theta plus theta. And then we add a constant at the end because we know we're supposed to. There we go. Yep.
When you put the integral of sine squared theta d theta, is that not supposed to be negative sine squared theta? Because
It is, but there's two minuses going on here, right? There, so like, I'll write it out. So there's
okay.
the minus from the formula, and so those two minuses cancel, going to sine squared, which then becomes the 1 minus cosine squared.
All right, thank you.
Mm-hmm. This is different, what just happened, right? So I call this one like it's an integration. I'll refer to this like generically as like it's a loopy, it's a loopy integration by parts. It looped, yeah. So there are problems like this, yeah.
Where did you get the 2 from? Like in front of the 2i? Or
I solved this. So take this equation right here, right? I have I. See this right here? I equals to that. So add I to the other side. I get 2i is equal to cosine theta sine theta plus theta. Now, I will admit to you guys, this is not how I typically do this integral. To me, this is the wrong way to do this integral. Okay? You're like, well, why are you showing us? Oh, man. I erased the, sorry about that. Well, I'm showing you because I think it's important to have more than one way to do an integral. Because everything that you, I mean, if you have two things to forget, then it's less likely you forget both of them, right? Yeah. So what's the other way to do this integral? Do you guys know? So this is actually 1/2 1 plus cosine of twice theta. D theta by trigonometry. Yeah? And then we can just straight integrate that. Because the 1/2 integrates to, you know, we got like 1/2 integral of d theta plus 1/2 integral of cosine of 2 theta d theta. So how does that integrate? Well, we get theta over 2. And this integrates to what? Plus 1/4 sine of 2 theta plus a constant. Which kind of looks like a different answer, right? You're like, wait a minute. This is math. We're not allowed to have our own truth that's come from our authentic stories. This is math, where truth is truth, right? There's one truth. We should agree on it. How can there be two answers? It must be that this answer is actually the same as the other one, right? Do you guys know? There's another trigonometry thing we should know, right? Which is this. The sine of 2 theta is equal to 2 sine theta cosine theta. If you don't, you know, to check on that, I always put in like theta is pi over 4. Right? If I put in theta equals to pi over 4 as a check, well, pi over 4 over 2 is pi over 2. Sine of pi over 2 is 1. Sine and cosine of pi over 4 are 1 over root 2. So I get 1 over root 2, 1 over root 2. That's 2 over 2, which is 1. 1 equals 1. Woo! So that's it. Now, how does that apply up here? So sine of 2 theta, well, so as you can see, the 2 and the 4 cancel, and we're back to the other answer, yeah? Which is a better answer? In terms of like, if you're implementing it in a computer program or something, I think that the answer we found from the other method's better because it's like easier, well, I don't know, but whatever, but it's like one sign function, right? So you've got one complicated function to implement. I assume multiplication by 2 on a computer is reasonably easy to do, right? You're like, anything is easy to do on a computer these days. What are you worried about? Suppose you want to make it fast. Imagine yourself making a computer program that needs to be fast. And every operation counts. You'd like the more simple formula. All right, so this is integration by parts. What do you have? Any guys have any questions so far? Should we do more? I think we should do more. So, you know, one of the artificial aspects of math textbooks is this. Math textbooks have problems at the ends of sections typically, right? So you work the integration by parts section, and then at the end of the section you have your integration by parts problems. So what are you going to do on those problems?
Integration by parts.
Integration by parts, right? But when you come to a problem in the wild, you don't know if it's integration by parts, if it's U substitution, right? Or if it's just something that's straight up nobody can do, you know? Now, you hope that your calculus instructor is not a monster, so he gives you problems that you can do on the test, right? But on the other hand, you realize that he does make typos sometimes, and there exists the possibility the problem doesn't make sense, so you always got that rattling around in your brain, right? But hopefully I'll give you questions you can do on the test. I think the quiz was the case, so. Okay, so I think I've spoiled this one then. I shouldn't have given that speech. Example 6. Integral of secant, let's use theta, d theta. So if we were to try integration by parts, what do we kind of have to try here? Short of some kind of sneaky business, I think I'm pretty much forced to make u equal to secant theta, right? And dv equal to d theta, which gives me v is theta. And du, what's the derivative of secant? Well, the derivative of secant is secant tangent, right? Derivative of secant is secant tangent. Okay, great. Then what? So I do my integration by parts. So then what happens? Well, looks like we got ourselves a theta secant theta minus the integral of v, which was theta. My du is secant theta tangent theta d theta. And so this is something that you guys have to deal with, right? Because you haven't taught calculus 2 a dozen times, and you don't know which ones are integration by parts problems and which ones are the other kind of problems, right? This is something you have to face. You have to try integration by parts sometimes on things that don't work. So it's important to kind of have a sense of, oh, wait a minute, this is going nowhere. Now, then again, maybe it will go somewhere if we try harder. I don't know. That's as far as I'm willing to go on this one in class. If you can keep going down this path and somehow make it loop or something, more power to you. I don't know if it's possible or not. I actually don't. The way I do this integral is by a deeper magic. I let u equal secant theta plus tangent theta. And if you do that, du is secant theta tangent theta plus secant squared theta, right? D theta. Which then gives us secant theta times tangent theta plus secant theta. D theta is equal to du, right? So solving that, what is tangent theta plus secant theta here, though? Well, that was my u, right? That's my u substitution here. And so that's u. So what do I have? I've got du over u, yeah, is secant theta d theta. which the first time you see this makes you go, whoa. Like I said, it's kind of magical. One of the best students I ever taught came to me at the end of like the first lecture in Calculus 2 when I did this, and he said to me, "Sir, doesn't writing u equals secant plus tangent assume the answer?" And I said, "Yes. Yes, it does, and you don't belong in Calculus 2. It's true. That kid. Anyway, it is, oh, secant squared. Good grief, what's wrong with me? Look at that. This is the weird thing, right? Integral of secant is actually really complicated. Integral of secant squared is what? It's just tangent, right? So it's a funny world we live in. Making the square is easier than not squared. But so integral of secant theta is integral du over u, which is natural log the absolute value of u plus a constant, which is natural log the absolute value of secant theta plus tangent theta plus a constant. This, my friends, is how we integrate secant theta. This is not integration by parts, right? But it is something we need to know. And it's really a Calculus 1 problem, but it's understandable and totally defensible if your Calculus 1 instructor never covered this. There are some classes I'd be teaching Calculus 1, 2, and I'd be like, not this semester, no, nope, nope, nope. I'll leave that on the plate of the Calculus 2 person. Because this one's tricky, right? Now once you see this, if I asked you to integrate cosecant, would you know how to do it? What would you try? If you saw this worked, if you were going to integrate cosecant, what would you try? I think I would try something similar, like, I don't know, what's the derivative of cosecant? So there's like a minus involved, right? Like, is the derivative of cosecant minus cosecant cotangent? See, I do these not often enough that I have to work it back out when I do it, but I don't want to get into it. I'm just saying, let me put some quotes around this. I'll just say something like this will solve that by pretty much the same kind of calculation, all right? I'll leave it to you guys to fiddle around with that because I want to get back to the integration by parts. All right, so excuse me. So the other problem, or am I on example 6? Or is this 7? I can't remember. 7? Whew. Never been good at counting. Integral of, let's say, x squared sine of 2x dx. How should we attempt to do this one? I think what I'm going to do, I'm going to put u equals to x squared, right? I'm going to put dv equals to sine of 2x dx. Now it's easy enough to overlook this, but the starting point of every integration by parts has to be identifying everything that's here as u dv, right? You can't leave anything out. If you do that, it doesn't make sense, right? You have to have all of it. This is all of it, right? Okay. So then what's my du? Well, du is 2x dx, yeah? What's my v? 1/2 cosine of 2x. Now, is that right? What have I missed? Negative, right? It's because the integral of sine is minus cosine, remember? Okay, so let's do it. We've got uv minus the integral of v du. This is the point in the lecture I started getting tired of writing down uv minus integral of v du, but I'm going to keep doing it for you guys. You're like, does there come a point where we don't have to write that down? Yeah. That's the point when you're confident enough that you're writing down what's correct. So be careful when you do it. It's usually usually as I make that kind of comment, I make a mistake. It's like, God has a sense of humor, I think. Let's see here, 2x du 2x dx. And then what happens? Well, let me clean up the minuses. I've got minus 1/2 x squared cosine of 2x. The 2's be canceling, so we've got, and the minuses be canceling, so plus the integral of, let's see here, x cosine of 2x dx. It didn't loop, right? But it got better, right? You know, we went from an x squared to an x. That's an improvement, right? Unlike the secant one I did over there, where we went from not having an x to having an x, and you can kind of get, well, having a theta, and you can kind of have a sense if we kept going, maybe we'd get more thetas if we kept going down that path. Okay, so then what? I integrate by parts again, right? So this time, I'll make this let me call this dv2, and I'll call x u2. u2 equals to x, du2 equals to dx, dv2 is cosine 2x dx. That makes v2 1/2 sine of 2x. And so then I do my integration by parts a second time. And so I'm going to have my u2 v2 minus the integral of v2 du2, which is all right, so u2 v2 is x over 2 sine 2x minus the integral of 1/2 sine of 2x times what was du2, oh, just dx. One more step, we're done, right? So we got ourselves to, and can you guys see that if I write one more line down?
I can.
Okay, okay. So minus 1/2 x squared cosine of 2x plus 1/2 x sine 2x. When I integrate the sine, I get minus cosine, but the minus and the minus cancel, so I get plus 1/4 cosine of 2x plus a constant. And there you have it. So the first couple of examples I did with like x e to the x or x2 to the minus x, if you think about it, if instead of having the x multiplying, we had x squared, you could still do it, right? And if I change this x squared to an x cubed, you could still do it, right? You don't want to do it, but you could, right? If I made this a 12th power, you could still do it, but then someone should pay you money, right? Well, then you should just be like, no, I will use a computer for that, you monster, right? So, but I think if you can understand it for the square, then you could understand it for the cube or whatever else. So like, I don't usually feel the need to explore this issue past like order 2. Any questions about this? What's the big question from all of these examples? Really, in a nutshell, is this: how do we choose u? How do we choose dv, right? But more basic than that, how do you know that you're going to do integration by parts? So here's a mnemonic that's generically speaking helpful. It's called LIATE. Now this is not something I invented. Like, I taught calculus 2 the first time, and the students told me this. I'm like, okay, whatever. Log, inverse, algebraic, trigonometric, exponential. Now, as a mathematician, this mnemonic makes no sense to me because these are not mutually exclusive categories. But the students think this makes sense, so I say, fine, I will share it with the other students. Since you guys told it to me, I will tell it to all future generations of my Calculus 2 students, as it seems to be helpful. So this basically says, choose u whichever comes first. So let's see how that played out in our examples, right? Example 7, I'll start with the last. I chose u as x squared. Why? Because I look at it, there's no log, there's no inverse. Algebraic, x squared is algebraic. I'm going to make x squared equal to u, right? If you go back to the examples I erased, there was an x in them. I made x equal to u. How about this one? Will this work for example? So example 5 is a funkier one, right? So you got no log, you got no inverse, you got no algebraic, trigonometric. We had to make, as you see, we had to make u equal to cosine. You're like, okay, well, yeah, but that didn't quite tell me that I needed to split the cosine squared into cosine cosine, but it still is relevant. Yeah, it's not a one-size-fits-all, algorithm here, but it does give you a sense of where you probably should go. This is irrelevant because it's not integration by parts, so I seem to have erased all my other examples. But anyway. So I think we're done for today, guys. So peace be with you. I get it. Uh-huh.